My dear friends, today we will see the numericals on beams. So this is the question paper from VTU FEM question paper for the year June July 2015. June July 2015. In that we will see the problem on beams. If you see, it is 7th B question. In 7th B question, for the beam and loading as shown in the figure, determine the slopes at 2 and 3 vertical displacement at a midpoint of the distributed load. Vertical displacement we need to see here. What is the vertical displacement? Vertical displacement we will solve in the another video. Here only we will see how to determine the slopes. And take Young's modulus is 200 gigapascal and moment of inertia is 4 into 10 raised to 6 mm raised to 4. The given problem is like this, like it is a cantilever beam subjected to UDL over here at a span of 1 meter, and it is fixed at first node and second node and third node. It has moment in x direction only, and whereas it is restricted from the vertical moment. Now we'll see how to solve this problem. Okay, we'll proceed with the problem. Let's see the steps. Okay, the given problem in this, we need to write the given data. The given data is nothing but here we have Young's modulus is 200 gigapascal and moment of inertia is 4 into 10 raised to 6 mm raised to 4. Here it has given the UDL intensity of load is 12 kilonewton per meter. So how to convert this in terms of Newton per millimeter? Here if you see, 12 into 10 raised to 3 is nothing but 12 Newton divided by, we have meter, we need to convert into millimeter, so we need to divide by 1000. If you cancel it, you will get 12. So 12 Newton per meter is nothing but intensity of load which is acting on the second element. In the previous video we have seen what are the steps which are involved in to solve the beam problems. Like here the first step is to modeling and discretizing the given beam, the given cantilever beam. We need to model, means here since we have UDL at a distance of span of 1 meter, we need to create a node over here. As we create a node over here, then we'll automatically it creates the second element. So in this problem we consider this cantilever beam as two elements, which you can see here. This is the first element and this is the second element, and these two elements are connected between three nodes, node 1, 2 and 3, and each node has the displacements which we can see here. Let the vertical displacement V1 because of force F1 and vertical displacement V2 because of force F2 and vertical displacement V3 because of force F3 in node 1, 2, 3 respectively. Similarly, we have angular displacement theta 1 because of moment M1 in node 1, angular displacement theta 2 due to the moment M2 at node 2, and angular displacement theta 3 due to moment M3 at node 3. This is how the modeling has to be done. Clear? These are representing the angular displacements. Clear? Okay. Once we do this modeling, the next step is to determine the stiffness matrix for each element. Since we have two elements, we need to determine the stiffness matrix for each element. Stiffness matrix is given by, as we earlier seen, E into I divided by LE cube, Young's modulus into moment of inertia divided by length Q, length of the element, and 12 6 LE minus 12 6 LE, and you need to remember only the upper diagonal elements. If you remember these upper diagonal elements, the same diagonal elements, lower diagonal elements will be the same. right? This is how you need to remember. Anyway, to solve the problems on the beam, you need to remember this stiffness matrix. So these are the elements. You go through it once, you pause the video, you go through these elements, and you substitute the values of ei is this L, and here we have L square, here we have L is nothing but length of the element. So once I will read here, see 12, 6 Le minus 12, 6 Le, 6 Le, 4 Le square minus 6 Le, 2 Le square minus 12 minus 6 Le, 12 minus 6 Le, minus 6 Le, 2 Le square minus 6 Le, 4 Le square, where Le is nothing but length of the element. Since we are calculating the stiffness matrix for first element, the Le is nothing but length of the first element. Clear? So substitute the data over here. That is nothing but cross-sectional area, Young's modulus is 200 into 10 raised to 3, moment of inertia 4 into 10 raised to 6, and the length is 1 meter, that is nothing but 1000, and it is Le cube in the formula. If you see, it is Le cube here, so here we have 1000 cube. If you simplify this, you will get the answer 800, and you need to multiply the lengths over here. So if you see our stiffness matrix here, you can see first one 12, no problem in that, we will keep it same. Here we have 6 Le, so what we have done, 6 into 10 raised to 3, 10 raised to 3 is nothing but 1000, 1000 is the length of the element. Similarly, we multiply the length wherever the length is given in this matrix. Once you calculate here, we have written 1 2 3 4 because as we know that the beam first element of the beam, this is the first element of the beam. Here we have node 1 and 2, and this node has vertical deflection and angular deflection. So that what we have, each node has 2 degree of freedom, 1 and 2. Here also we have 2 degree of freedom, so we can write 3 and 4. That is vertical displacement and angular displacement. That's what we have written 1 2 3 4. These are nothing but the displacements, vertical as well angular displacement. So we have 4 by 4 matrix. Similarly, we need to calculate the stiffness matrix for the second element. If you see the these are the same again. E is Young's modulus is same, moment of inertia is same, length is also same, so you will get again the 800, which we have written here 800. Here the elements, again these elements will be the same elements because we have the same length of the second element, we will get the same elements. Here the only change is these things, like these are different because as you know that again the second element which is connected between node 2 and 3, we have in node 3 we have 2 displacement, at node 3 we have 2 displacement, so each node has 2 degree of freedom, we will get 3 4 5 6. This is how we need to write. Once we write the second elemental stiffness matrix, next step is to determine the global stiffness matrix, where we need to add these two matrices. So since in the given problem, see if you see our problem, we have 2 elements, 3 nodes, and each node has 2 displacement, so we'll get here 2 displacement 2 2, so we'll get overall 6 displacement. In the sense, the global stiffness matrix should be 6 by 6 matrix, so that's what we have here. So 800 is the common for both the matrix, so 800 we have taken as a common. Next we have 1 2 3 4 5 6, 1 2 3 4 5 6. Clear? Once we do this, once we write, first we need to write these things, vertical and as well as horizontal. Once we define this, next we need to define the elements. How to define the elements? In the previous video, if you see, I have explained very clearly. Here once again we'll see. For example, if you want to define this element 12, what we need to do, we need to see the first row and first column. First row, first column is 12. How this 12 has came, we'll see. First we need to go for the stiffness matrix for the first element. Here we have first row and first column 12, but if you see in the second element, we don't have first row, we have third row, we have fourth row, we don't have first row. So we have only in the first stiffness matrix we have first row first column, that is 12. That's what we have written here, 12. Similarly, for example, if you want to find this 24, how this 24 has came, we'll see. Like this 24, it is at third row third column. Third row third column, how we need to calculate here? If you see here, this is our third row, this is our third column, we have 12. Similarly, if you see in the second stiffness matrix, we have third row third column, we have 12. 12 plus 12 is nothing but 12, 24. Like that we need to calculate each and every element. First you need to calculate this. Once you calculate the elements in the row, next the thing is you need to write the same elements over here, because the stiffness matrix is a symmetric matrix. See here, 6 into 10 raised to 3 we have written same, minus 12, 6 into 10 raised to 3, here 0, here 0. Once you determine this, next you need to go for 2 by second row second column, that is nothing but this one, second row second column, that is nothing but 4.6, 4 into 10 raised to 6, and these element you need to calculate. Once you determine this element, again the same thing you need to write. See, the same elements which are copied. Next you need to determine this third row third column, these elements. Once you determine these, the next step is the same are copied here. Next we need to determine the fourth row fourth column, this. Next these two elements, once you determine, the same element you need to copy. Fifth row fifth column, this you need to determine, this you need to determine, the same you need to copy. Next sixth row sixth column, you will get this answer. Once you calculate the global stiffness matrix, the next step is to write the equilibrium equation, that is nothing but K into U, which is equal to F. As we know that stiffness is nothing but load by area, load by displacement. Before that we have some like we need to define what are the global displacement vector. As we know that v1 theta 1 v2 theta 2 v3 theta 3 are nothing but the vertical displacement as well angular displacement. See here, this v1 is due to force F1, this theta 1 is due to moment m1, v2 is due to force F2, theta 2 is due to moment m2, v3 is vertical displacement, theta 3 is angular displacement due to force F3, moment m3. And this is a transpose matrix. Similarly, global load vector is nothing but again F1 m1 F2 m2 F3 m3. Here we have this because here we have two elements in the sense 3 nodes. 3 nodes means we have 6 loads. At each node we have 2 loads, that is force and moment. As we know that the second element is subjected to UDL. To calculate the UDL force, we have the formula which we have seen in the earlier video. This formula is only used whenever the beam is subjected to UDL. Here we have PL by 2, PL square by 12, PL by 2, and we have minus PL square by 12. If you see this formula here, this F2 is nothing but second element. F2 dash is nothing but UDL force is applied at a second element. That second element is connected between node 2 and 3, right? So here I can write this as 3 4 5 6, because at the second element node 2 and 3 we have second element, we have two displacement, that is 3 and 4, because first node has 1 and 2 displacement and second node is having 3 and 4. So I have written 3 and 4. Here we have 5 and 6 displacements. So that's what I have written, 3 4 5 6. Here P is nothing but intensity of load, that is nothing but load, ODL load, that is 12 kilonewton per meter. So we have converted that. If you convert a kilonewton per meter into Newton per meter, you will get 12. Since it is acting in the negative y direction, we have taken minus 12. So minus 12 is the P. Length of element is, second element is 1000, so 10 raised to 3 is the Thigmot length divided by 2. Similarly, minus 12, L square is 10 raised to 3 whole square divided by 12. Minus 12, 10 raised to 3, 12. If you substitute all this data, you will get this answer. F2, M2, F2, M2, F3, M3. Nothing but the forces due to this. At node 2 we have this vertical force, angular moment, vertical force, angular moment. That's what we have written. Vertical force F2 we have, angular moment theta 2 we have, vertical force we have F3, angular moment we have M3. If you solve these, you will get these equations, right? Once we have this global load vector, the next step is to form the equilibrium equation. This is the equilibrium equation that already discussed. K into Q is equal to F. Once you substitute the global stiffness matrix, global displacement vector and global force vector, once we write all this, next step is to apply the boundary condition. We apply the boundary condition to the equilibrium equation. If you see our problem in this, if you see the given problem here, the node 1, 2, 3, node 1 is fixed, node 3 is fixed in the vertical direction, node 3 is fixed in the vertical direction, whereas horizontal we have moment. So here V1 is fixed, theta 1 is fixed. Here V2 is fixed, whereas theta 3 is movable. Here V3 is fixed, sorry, theta 2 is movable, V3 is fixed, theta 3 is movable. Here means we have horizontal displacement, vertical displacement are restricted by these supports. Clear? So the same thing which we have written over here. The first node is fixed, means the V1 is fixed, theta 1 is fixed. First row, first column we need to element. Similarly, second row, second column we need to element. Again, we need to eliminate the vertical displacement, that is nothing but, here you can see it is very easy to eliminate. V1 is fixed, theta 1 is fixed, V2 is fixed, V3 is fixed. V1 theta 1, again V3 V2 theta 2, sorry, V2 and V3 is fixed. So we left out with only these data, theta 2, theta 3 here, and here we have M3 and M2 and M4. Those left out equation which we have written. Once we element rows and columns, we will get this matrix. Here 800 which have taken common, again we left out with this one and as well as this. Here 1, 2, 3, 4, V1 theta 1, V2 theta 2, V3 theta 3, right? V1 theta 1 is fixed, V2 fixed, V3 fixed. So theta 2 theta t is left. This is nothing but theta 2 theta 3. Here also theta 2 theta 3. So here we will get M2 M3. Those things we have written here. And here row into column, if you multiply row into column, you will get these two equations. If you solve these two equations, you will get theta 2 as minus 2.67 into 10 raised to 4, theta 3 as 4.46 into 10 raised to 4. These are nothing but the in radians. These are the slopes which it is asked to determine. Now in the next video we will see how to calculate the vertical deflections in the UDL. When the element is subjected to UDL force, what are the vertical deflection due to the application of this load, we will see in the next class. Now we have seen what are the angular displacement which are caused due to this loading condition. So if you have any doubt, if you are not understanding anything from this video, you just comment below so that I can make a better video than this. Thank you for watching.